Okay, so I'm going to show you guys some related rates involving spheres. So two things that we need to know are the formula for surface area and the formula for volume of a sphere. Those will usually be given to you on the AP test when you need to use them, but we're going to use them a lot today. So I've put them on every single slide that we're going to go through. So the first question says the radius r of a sphere is increasing at a rate of 2 inches per minute. So remember, increasing means that it's going to be positive, and 2 inches per minute. The radius is increasing, so we're going to call that dr dt. dr dt is going to be 2 inches per minute. Find the rate of change of the volume. So we want to find dv dt equals something when r equals 6. Now keep in mind, r equals 6 is not a constant. That's just the specific point in time that we're looking for. So we want to make sure that we don't plug anything in here until we take the derivative. So we're dealing with volume, so I know I'm going to use my volume formula. So we know that volume is going to be 4/3 pi r to the third. Derivative here. Oops. So when I take the derivative, I'm going to multiply this. Okay, so dv dt. Remember, pi is just a constant, so really our only variable here is r, and this whole thing in the front is basically just a coefficient to the variable r. So when I multiply that through, 4/3 times 3, that's going to give me 12/3, which is just going to be 4. Pi r squared now, and then we got to put r dr dt. Okay? Now that we have all that information, now we can go and plug in what we know. We don't know dv dt still. 4 pi, I know that I'm talking about the instant when my radius is 6 inches. I'm going to put the units in there just so that we can make sure that we see where the units come from, squared. And then dr dt, it was increasing at a rate of 2 inches per minute, so we're going to say 2 inches per minute. And we're just going to multiply that all the way through. So dv dt, I'm going to go and take my calculator. Actually, we can leave this in terms of pi. So 6 squared is going to be 36. Okay, 36 times 2 times 4 is going to be 288. And I'm just going to leave it in terms of pi right now. Now I'm going to have inches squared, and then I have inches there, so that's going to become inches cubed over minutes. So inches cubed per minute. And that's our final answer. Now you might see it left in terms of pi, and you might see it actually written out. So that's going to be approximately. Now in calculus, we always round everything, no matter what we do, to 3 decimal places. Okay, so make sure it's always rounded to 3 decimal places. And that's going to be the rate of change of our volume at that specific point in time. That's the rate that the volume is increasing at, because it's positive. So we're going to know that that volume is increasing. Okay. Next one. After using an experimental drug, the radius of a spherical tumor is observed to be decreasing. Ooh, so decreasing, we know we're going to have something negative there. At a rate of 0.1 centimeters per week when the radius is 2 centimeters. At what rate is the volume of the tumor decreasing? So we know, let's see, we know that the radius is decreasing. So dr dt is going to be negative 0.1 centimeters per week. We know that the radius is 2 centimeters at that point in time. And we want to find dv dt again. So this one's very similar to the last one. So what I want you guys to do is to pause the video right now and to see if you can figure it out completely on your own without my help. All right, so what we should have done here, we know that volume is 4/3 pi r to the third. So I know that dv dt, I'm going to use my power rule. I'm going to come out with 4 pi r squared dr dt. Okay, and then I need to go and I need to plug in what I know. So I don't know dv dt. My 4 is going to stay. My pi is going to stay. My radius is going to be 2 centimeters squared. And then dr dt I know is going to be negative 0.1 centimeters per week. Okay, so from looking at this, I know that my units are going to come out to be centimeters to the third, so centimeters cubed per week. So let's go ahead and do that in our calculator. And that's going to come out to be negative 1.6. And I'm just going to leave the pi there for right now. Centimeters cubed per week. Okay. And then we can also approximate that, multiply that by pi, and we get negative 5.027 centimeters cubed per week. So that's our estimated volume, or estimated rate of change of the volume. So notice it's negative, so that's going to tell me that this tumor, the volume of the tumor is actually decreasing at that rate, negative 5.027 cubic centimeters per week. All right, next one. The radius of a sphere is decreasing. Oh, we got decreasing again. Decreasing at a rate of 2 centimeters per second. So we're going to say dr dt. I always like to make a list of everything I know. Centimeters per second. At the instant when the radius is 3 centimeters. Okay. What is the rate of change in square centimeters per second of the surface area? So we want to know what ds dt is. I'm just going to use s instead of sa. So we want to know what ds dt is at that certain point in time. So let's take, we know that s is going to be 4 pi r squared because they gave us that, and I told you that, guys, that at the beginning. Derivative, because we need to know the rate of change of each of these things, is going to give me 8 pi r, and that's going to decrease to a 1 dr dt. Okay, and then we're going to go and we're going to plug in everything we know. So ds dt is going to be 8 pi, my radius was 3 centimeters, my rate is negative 2 centimeters per second. Okay, so you can see here that we're going to get square centimeters because we have centimeters squared. So that's going to be 8 times 3 times negative 2 is going to give me negative 48 pi centimeters squared per second. Or we can multiply that by pi, and we'll see that it's negative 150.796, always 3 decimal places, 796 centimeters squared per second. Okay. All right, last one. You guys see if you can do this one on your own. Pause the video, see how far you can go on your own, and then play the video and see if you can get it from watching it. So Calvin starts filling up a spherical water balloon. The radius is increasing at a steady rate of 0.2 inches per second. So we know dr dt is going to be 0.2 inches per second. At the instant when the surface area becomes 100 pi, so I know surface area is 100 pi square inches squared. What is the rate of increase of the volume? So we need to know dv dt equals what? Okay, so we're actually going to use the surface area and the volume equation all in this problem. So if I need to know dv dt, I know that I'm going to start out with my volume formula. So let's start out with the volume formula. Let's take purple. Oops, we already used purple. Let's take blue. So if I need to know dv dt, I know volume is going to be 4/3 pi r to the third. So dv dt is going to be 4 pi r squared dr dt. So I know that much. Now, let's go and start plugging in what we know. So I know dv dt is what I'm trying to find, is 4 times pi. Now, they didn't give me the radius here. I have no idea what my radius is. But I do know that dr dt is 0.2 inches per second. Okay, so I know that much. So now what I have to do is I gotta say, okay, well, they gave me this extra piece of information. Is it possible for me to use the surface area to go and figure out what that radius is? Yeah. So I'm gonna go over here to the side, okay, and I'm gonna say, all right, well, if surface area is 100 pi, 100 pi has to equal 4 pi r squared. So let's divide by 4 pi, divide by 4 pi. They come out with 25 equals r squared. So I know r equals 5. And it's going to be 5 inches here. Okay. So they just gave us that extra little piece that you had to go and figure out on your own. So dv dt is going to be 4 times 5 times 0.2, which gives you 4 pi. 4 times 25 times 0.2 is going to give me 20. 20 pi inches squared, inches cubed per second, which is going to be approximately 62.832 inches cubed per second. So that gives us the rate of change of the volume. So we had to do a little bit of extra work there to get what we needed, but always start out with what's the question asking. So the question was asking the rate of increase of the volume. So we always want to start with that and start solving for the rate of change of the volume. And then if there's a piece of information that's missing, see if they gave you enough information to try and go back and figure that out. Okay, so that's your related rates with spheres. Okay, really, as you continue doing this, you're going to notice that the process is the same no matter what shape, no matter what I give you. You just have to figure out what's the equation that I'm using, find the derivative with respect to time, and then plug in everything that you know.